Shall I? OK. Welcome back to the afternoon session. My name is Markus Weimer. I'll be the first speaker in this session. I'm going to talk about REEF, a project that we've been doing at Microsoft in the Cloud and Information Services Lab over the last 2 years. I want to start by motivating why it exists and what we are doing. So there we go. You probably have heard a lot about resource managers like Jan and Mesos and stuff like that during the talks earlier today and yesterday. For the purposes of this talk, I use the following kind of symbolism. The right-hand side is the never-ending cloud, and all these rectangles are individual containers. Right? This is a little bit more abstract than drawing little boxes with machines. OK, so why are resource managers cool? Resource managers are cool because they enable true multi-tenancy on 2 dimensions. Number one is, for the same user or same access privilege, you get multiple workloads. You can run a streaming job right next to a batch job, right next to an interactive job, and all that kind of stuff. Secondly, you get multi-tenancy in the true sense of the word, that you get to run many users on the same cluster. You can have a production job that needs to finish in the next hour right next to an exploratory data scientist's job. But there's a big but here, and that is we need to rewrite or rethink how we write our applications, our big data applications, on top of resource managers and how to react, how to live in this world. I want to walk through a couple of examples of that. So if you think about you are running a job in these blue rectangles, and then, of course, disaster strikes, right? Some machines disappear. You have to deal with that somehow in your algorithm or in your system. The other situation might be someone else just has plain more money and takes away resources from you. So then you might get a preemption event, and you need to do something about it, right? Either treat it as a node failure or do something smart about it. The other situation might be you might be the lucky guy with the more money, and you get more containers for your computation, and you get to scale up, so you want to be positively elastic. Now, I want to walk through a couple of examples of how this manifests itself in kind of this high-level view. If you write a SQL engine or a MapReduce engine on top of a distributed file system, you might find yourself loading some data, applying some operators, and in order to achieve fault tolerance, you write things to disk once in a while. Or in case of the traditional MapReduce library, you write to disk all the time in case of failure. So that's how you get fault tolerance. Then you might hit the join phase, and you realize, oh my gosh, I have way more data than I anticipated. My mappers actually produced more output than input. I need to be elastic at that very moment and scale up. Right? This is a requirement that you have if you write applications on resource managers. Another example that's very dear to my heart, because I'm a machine learner at heart, is if you write machine learning algorithms or systems on top of a resource manager, you want the 2 above, right? I mean, things disappear, and you want to be elastic, and if containers are free right now, you want to make use of them. But you might end up in a situation where, or you actually will end up in a situation where you load some data, and then you want some iterative computation on top of it. So there are tons of people who have done this in the past, right? And back at Yahoo, we had the saying that there are these Hadoop app users who just write a map-only job to get this done. But this is a need that people have on top of resource managers. Lastly, another large class of applications is you run a graph processor, right? Then typically you partition your data into containers, and these containers then start sending messages to each other. Different from, let's say, MapReduce, the messages are typically small, so you care more about latency than throughput. OK, we are not the first people to recognize this, right? For most people in the room, for each of these examples, you had a system in mind when you were seeing this example. Like, oh, the first one is MapReduce. The second one, maybe Spark. The third one, oh, this is Giraffe, right? So we are not the first to recognize this. And thankfully, with resource managers, what we have achieved is that all of them run on the same cluster, right? We don't have to buy a Giraffe cluster and put it next to the Spark cluster and put that next to the Hadoop cluster. They can all run on the same cluster. So they happily run on the same clusters. But now we have created another form of silo. It's no longer the hardware silo, but it's the software silo. Each of these took a really long time to build, because if you build any distributed system, you want base functionality like knowing whether or not a machine is still around. You have basic requirements like, I want to send some data to one of my compute nodes. This is completely independent on whether you run a graph processor or a MapReduce engine, right? Everyone had to build this to get to that point. The other problem is that in practice, these various forms of programming models form pipelines. There isn't a machine learning problem in the world that doesn't require, or at least should have, a SQL-like feature generation phase up front. Right? So even though you might have a beautiful system to do machine learning, you have to now use external coordination like USI to set up the pipeline, because every real-world job is a pipeline across these frameworks. As much as we, from a research perspective, would like that all people agree on one abstraction that they write their software in, that doesn't seem to happen. So we end up in these multi-framework pipelines, and the best thing we can do today is to orchestrate them from the outside. Orchestrating them from the outside means at the end of each job, you write all your output to HDFS, and then you schedule the next programming framework which picks it up from there, and you start running. Right? This has two massive overheads. Obviously, you need to write to disk and read from it again, but also you need to reschedule the next job, and you have a blocking handover. You need to wait for all the data to be written before you schedule the next guy. So let's see whether we can improve upon this. This is where REEF comes in, and there's a convenient way to think about it that Carlo Corino, one of our team members, came up with. And that is, if we say the resource manager and the distributed file system, let's say Yarn and HDFS, and call that the cluster operating system, then a good way to think about REEF is the standard library. It doesn't matter whether you write Word or Photoshop, you need a memory allocator. Right? There is a standard library on an OS, and we need a standard library for clusters, and this is our proposal. I'm very sure that there will be others. Okay, so we want to be broad in applicability, which means that wherever possible, and that's currently always, we put mechanisms over policy. In REEF, you will not find a policy. So for example, when a node goes down, what REEF does is it tells you about it. So this machine is dead. There's no automated fault tolerance. There's no restart of your job anywhere. You have to then react to that event. That's burdensome, but it also is flexible, right? You can choose what you want to do then. The other thing that we obviously want to achieve is we want to avoid silos. We want to create a world in which we can hand over containers with data in them from one framework to the next, such that, let's say, a SQL engine writes some output at the last step. Let's say it was a reduced step. And then you put in the machine learning code right in place, sit on top of that data without loading it from disk again, or without even starting another process. You just send a different task into the same process. Lastly, especially given that I'm from Microsoft, we want to work on this JVM, CLR, everyone else divide. Most of you in the room might have used Hadoop streaming, and Intel is very happy that you do, because there are many overheads associated with that. We want to work on that, and we have some really cool solutions there that are unfortunately not part of this talk just because of time. So if you take the last 10 minutes to ask me about that, that would be very helpful. Okay, so now let's talk about what REEF actually does. So within each REEF job, we assume that a resource manager exists. Right? We do not replace the resource manager. We do not fork it. We just assume, for the purpose of this talk, that there is Yarn. So Yarn exists in our cluster, and it does what Yarn does. Right? It handles the resources, it handles quotas, it handles job admittance, and all that. We have no business in that. Everything in REEF is part of your job. Nothing in REEF is installed on the cluster. Then per job, we have what we call a driver. And for those of you familiar with the Yarn terminology, this is our application master that we provide. The driver's job is to request resources for the computation, coordinate the computation, react to failures, react to job completion, stuff like detecting that you are done and that you can shut down, right? This is user logic. Lastly, when the driver in this case asks for 3 containers, which are where the data is, and 3 additional ones, in this case, the stars align and the cluster has exactly those resources available that we ask for. We instantiate what we call evaluators in those containers. An evaluator is a long-running process that we install in each of the containers, and it lives for exactly the time that you hold the allocation of that container. So when we get an allocation from Yarn, we start an evaluator inside, and when you shut down the evaluator process, we return the allocation. So there's a one-to-one mapping, but it's a process. It's not just the right to run something, it is actually something running. And what's running inside are tasks. And the driver gets to put the tasks into the evaluators, right? In this case, we have 6 tasks running. And as fate might have it be, one of the evaluators crashes, right? It disappears from the network. You receive no heartbeat. Yarn tells you that it's dead. Through some mechanism, REEF learns about the fact that this machine is dead. And then we fire an event to the driver where user logic will receive that event and react to it, right? This is not easier in principle than any distributed system. It's just ultra convenient that you have exactly that event in exactly that place, because making it so is hard. So in this case, the driver decides that this task was really important and goes ahead and asks for another container. We instantiate an evaluator inside, and the task is reinstantiated inside of that evaluator. But other choices would have been possible, right? If this task was basically done and another task is also basically done, you might reshuffle that work to another container that you already have. Of course, another situation is that a task is done inside of an evaluator, right? You send a task there, it computes something. Let's say it is a map task that runs something on a block of data, and it's done. Then it reports back to the driver, says, hey, I'm done. Crucially, at that moment, the container is still around, and the evaluator process is still running. Even more so, we have abstractions inside of the evaluator process, such that a task can leave information behind for the next task. So we don't support running multiple tasks at the same time in one container, but tasks that run sequentially in the same evaluator can hand over state from one to the other. So now the upfront task could have been MapReduce, the downwards task could have been a machine learning task, right? We support handover of data and the compute node natively. Okay, in this case, the driver goes ahead and instantiated some more computation. Okay, we call this retaining evaluators. We hang on to them, which gives rise to our name. It's REEF, the Retainable Evaluator Execution Framework. And where that comes from, well. Okay, so why is retaining evaluators cool? There are a couple of examples that I already mentioned, and I just want to visualize them. So number one is, it's often very convenient to use MapReduce as a paradigm for data partitioning. The shuffle step in Hadoop is really good, so why wouldn't we use it to do a random partitioning of data, let's say, because a downstream machine learning process requires it from us. Then we take this MapReduce job, the mappers go away, but we replace the reducers with the machine learning task. Right? The data is already there, it is shuffled, it is in main memory. We have zero overhead of doing that. And then, of course, we can set up an iterative computation on this, where either the task is long running and we do something like MPI on top of it, or where the tasks come and go, and that's how we implement the iteration, depending on how the computation is structured. Lastly, you can, of course, also take data, load it into, a couple of evaluators, and then send tasks there for interactive querying. Right? So from your laptop, you can send tasks there, and they will execute, and you get some output out. So it's also very handy for that kind of interactive experience. Okay. So I walked you through kind of the high level of a REEF control flow, and I want to stress a few points. I believe that it is fairly easy to reason about as far as distributed programming goes, because we centralize everything in the driver. Whenever a machine becomes available, we fire an event. When a machine crashes, we fire an event. When a task is, we can confirm that a task is running, we fire an event. When the task is finished, we fire an event. There are like 25 events or so that you can listen to. And all of those are centralized in the driver, and you have one place where you can reason about it. Right? This also enables centralized error handling. So when a task throws an exception inside of an evaluator, we capture those exceptions, serialize them, send them across the wire, and present them to the driver. This follows from the logic that if the driver is the central place in the control flow, it should know how to deal with the exceptions that the task code couldn't deal with. Right? Similarly, when an evaluator crashes, we also, if it is due to an exception, we capture that exception, send it across the wire, throw it at the driver. And some of you might think, hey, this one driver in the middle will eventually be the bottleneck, right? That's true. I mean, it's one machine, and the one machine has to orchestrate the control flow. But remember that the job tracker in Hadoop 1 was also one machine that orchestrates the control flow for tens of thousands of jobs running on thousands of computers. So if your application requires tens of thousands of tasks running on thousands of evaluators, we might get into the scalability bottleneck here. Until then, I'm fairly confident that the design will hold. And of course, then, because it is an event-driven program, there's nothing requiring that all events are processed on the same machine, right? We couldn't then start thinking about splitting the driver onto multiple machines. Also, and this is more in a foresight feature, the REEF layer itself has almost no state. So whenever we get a heartbeat from an evaluator, that heartbeat is complete. It's not just a delta heartbeat about what changed since the last one. This is for a feature that we are working on right now, which is driver restartability, work-preserving driver restartability. When a driver disappears and comes back online, it needs to rebuild the state that it has. And the less state we have, and the more of which we can recover by the natural occurrence in the cluster, the better. So if you want to build an HA application master or driver, REEF will not stand in the way of that. It's still tricky to build an HA driver, right? But REEF will not stand in the way, which is the best we can actually do at that level. Okay, we built 2 support libraries as part of REEF that are also available separately, and I think they are useful separately. One is Wake, which you can think of as a more static version of RxJava. So we do event-driven programming, where events originate at some event source and then some destination handles them. For example, REEF is the event source for the allocated evaluator event, and then user code reacts to that. But we know about the subscriptions of event handlers to events at static time. When you submit a job, we know about this. It's not a runtime thing. This allows for all kinds of optimizations. At the very base level, we free write on the JVM inlining, right? So instead of having virtual function calls, the JVM will know straight away that it can optimize all of this away. The implementation underneath, for those of you who know SEDA, the Scalable Event-Driven Architecture, it's basically that plus thread sharing. So in SEDA, you have stages, and each stage has a queue in front of it, and a centralized scheduler that decides which stage gets how many threads to process the queue, right? And a very good heuristic is to always assign the thread to the longest queue. And that's often good. In the case of very small events, very small event processing, the thread switching cost is too expensive, in which cases we support using the same thread from event originator all the way to processing it. The other project that we did is Tang, and Tang is our configuration manager. And you think about, we are a research lab. Why do we care about configuration? Well, we care about it because it's damn hard. If you write a Hadoop job today and you misspell the size of your map memory, then just the default will be used and you will never know about it, right? If you misspell parameters or you use values that are illegal, there is painstakingly code put in place to check for that, right? Would be cool if that was automated. So in Tang, we look at this and solve it in a very interesting way. The other thing that we recognize in the design is that the process, the program that configures, is not the program that executes the configuration. So you have a driver configuring evaluators. You have a client configuring a driver, right? You need to send this configuration across the wire, and another process evaluates it. So it would be helpful if the sending process could tell you whether or not this particular configuration has any chance of success on the receiving machine. Because then you don't have to waste a machine decade for all the machines to boot up and throw you the same exception, right? So how do we attack that particular problem? We view configuration as dependency injection. So for those of you who are familiar with Juice or other dependency injection frameworks, it's a very natural thing, and I will walk you through an example. So let's say this evaluator threw you an exception, and if you are doing any of these string-string map style configurations that are very popular, the following exception might be something that is expectable, right? You get a null pointer exception because you try to get something out of a hash map. The return value was not there, so it's null, and then you use it, and some 10 lines later, you get a null pointer exception. So you have to go there, and then the next thing that I would do is instrument this code to print out what exactly was null, how was it used, and all that, right? That's why there are so many log statements. What if you could instead get this error message? There is a parameter named command specified in the configuration file, but it's not used. There is another parameter called CMD that is required, but it's missing. Now you immediately know what to do, right? And you get this way before you send the configuration. So how do we make this happen? So first of all, let's fix it. So now we say CMD equals ls instead of command. And then we have a shell task, which is a task that executes a command, which we say depends on a parameter called CMD. And we write this up in code such that we can reason about it. Then another kind of error you might have is you try to use that in place of an evaluator. Then you get another kind of exception where you say, hey, you try to configure a shell task where an evaluator is requested. This doesn't work. So let's bind a task. What this figure means is when I walk up to the configuration mechanism and say, give me an instance of task, which is an interface, return a shell task, and I can return a shell task because I know what the parameters for the constructor are, right? And then you can walk this completely through and build up the complete graph. And this is literally the configuration graph that you have in an evaluator in REEF. So we only ask for an instantiation of an evaluator, which depends on an implementation thereof, in this case, the yarn evaluator. That depends on a task to run anything, where the user told us which task to run. Now, if you have this configuration, you can think of it as make for objects. And something's missing, or something is misleading, or disagreeing with each other. You can do this by just looking at the data, right? You don't have to run this to know whether your job has any chance of success. OK, so far for the REEF control plane and things that we built to make the control plane happen. And I should say that Wake and Tang are both available in both .NET and in Java. And they are cross-compatible. So you can evaluate a REEF configuration file that's meant for a .NET process from Java and get exceptions about whether or not the .NET runtime will be able to instantiate things. Now on to the data plane. I should say that everything up to now exists, is downloadable on our website. Most of what I'm talking about now is under heavy development, to say the least. So of course, the control plane is not everything in a big data application. You also want to do something with data, right? That's why you started the big data application in the first place. So let's talk about a couple of things that we are working on in this data plane. One is you want some form of fault-tolerant communication. Let's say you have A and B talking to each other. A and B are tasks. And B disappears, right? At the very least, you want to notify A. And when B is reinstantiated on another evaluator, you want to notify A where to send the information now. That means you need a name service, you need some detection mechanisms, and stuff like that. And we have that. The other way of doing this is A delivers stuff to a mailbox of B, and when task B becomes available, it checks the mailbox and downloads the messages for it. Right? We don't have that. Contributions welcome. The other thing that many applications need is a form of group communication or shuffle. And I will talk more about group communication later. And you, of course, I mentioned I motivated this at the beginning. You might want some low latency communication with loose-and-goose error handling, but really low latency, really fast. We do have a checkpointing library for REEF on, again, both .NET and Java. The checkpoints here are on a per container basis. So if you want coordinated checkpoints, that's one level up in the application level. Right? OK, let's talk about group communication. And I want to do so in an example. And the example stems from the domain of machine learning. And for all of you who have done machine learning projects in the past, please don't throw tomatoes. I'm going to do this at the very basic level. Let's say you are given a data set, X of examples. And each example contains of a feature vector X. That's just features that this data point has, let's say word in an email, and a label Y that tells you whether or not someone clicked on it, whether or not it's spam, stuff like that, right? Now we want to find a predictor, and a predictor is a function f of x such that f of x is close to y for unseen data, right? That would be nice, right? That's the problem of your spam filter that Google or Yahoo or Hotmail solve for you every day. They look at your mail and they say, it's likely spam, it's likely not spam. So what we want to find is, and I'm making a simplification here, we want to find the function that minimizes the quadratic distance between the two, right? We say f of x minus y is how wrong we are. We make that quadratic to make it always positive. That's what we are looking for. We are a little bit in trouble because the set of functions is not even countable, so we will not find the right one. Searching in this space is a bit hard. So what we do is, OK, let's make it a really simple assumption and say, our functions are actually just linear combinations or weighted sums of the input features. Now we can replace the search for the perfect function with the search for the perfect vector. And lucky us, this problem is what's known as convex in W, in this weight vector, and we can have algorithms that search for it. Now, one of those, OK, and this is the objective function that we want to minimize. One of those algorithms is known as batch gradient descent or just gradient descent, where we say, in each step, so we start with a random weight, right? We just assign 0 to everything, or we make one up. And then until we converge, we say, let's compute a gradient, which tells us in which direction we need to improve the model to make progress. And let's then apply that gradient to the model to get the next model for the next iteration. Right? This gradient computation you see here is a sum over all data points. Sums over all data points are awesome because you can just parallelize them, right? You can just chop your data into partitions, put some partitions on various machines, and each machine produces the partial sum. You send that up an aggregation tree, and you have the sum. This is wonderfully parallelizable. So in MPI lingo, this would be a reduce operation, right? Every machine produces the input to the reduce tree, and then you get that into some place where you perform the update. And this result of the update is then needed on all the machines again, so you broadcast that. OK, so we need reduce and broadcast to make this algorithm go on parallel systems. So how do we do this on REEF? On REEF, you would have a driver that requests some evaluators. And then for the sake of simplicity, let's just assume there's no framework up front. We just send a load command. So we set a task that loads and parses the data into main memory. Then we have it in main memory, and we can start the actual computation. But there's nothing here that says that load and parse needs to be the thing up front, right? It could be, for all we know, a complete Hive program. And then the driver allocates another machine, which handles the update function. And they start communicating in broadcast and reduce sequences, right? The master sends out the current model, and the machine, the slaves compute gradients and send them up. And of course, in real life, you do this with an aggregation tree and with slightly smarter setup than just sending everything to the master. Now, a real interesting situation arises when a node fails. Right? In traditional MPI, node failure in the worst case means that your application hangs. In the best case means it crashes. So given that we are in the cloud where node failure and preemption is the norm and not the exception, and we didn't pay millions of dollars to Cray to make these things go disappear, how do we deal with it, right? So one thing that we are working on is to say, OK, we expose these events to the application, and the application deals with those events when machines come and go. So whenever a machine disappears, we make it so that the application knows about it, but we still compute the outcome of this iteration of the algorithm with just less machines. Even more so, we make it so that from the perspective of the application, this particular group of MPI or MPI-like calls is executed as if that machine wasn't part in the first place. Right? So there's an atomic guarantee here where you say, I'm entering a critical region. Within it, you run, and then you get an outcome. And when you get the outcome, you get told which machines took part in this operation. And then the algorithm has choices, right? It can either rerun that part of the computation, or it cannot, or it can do all kinds of things. OK, so when the machine comes back, we, of course, also make it only part in the next iteration. It will be added not in the middle, in between any of these steps. So we have a begin and end statement where you say, for these blocks, please make it so that nothing voluntarily is added to my computation. And if something is involuntarily removed, tell me after it. OK. Now on to the one graph that I have in all of this. And this is, we tried this with a very particular setup. We used this machine learning algorithm that I spoke about earlier, actually a slightly more sane version. And what we did is we said, OK, we go to a real Hadoop cluster. We request 255 containers. Then we wait till we have all of them. When we have all of them, we load the data into each of them. And then we commence the algorithm. That's the red line. And the x-axis is time, and the y-axis is how good the current model is. Now, the green line is an idealistic cluster, right? We get all the machines at once instead of trickled out over time when other jobs vacate their computation. And we get them all at once, and we ask them all to load data at that very moment. When we do that, we still have some contention on the network, right? Because all the machines load stuff at the same time. But this is considerably faster, but those clusters don't exist, right? Where you just walk up to and no one else is using it, and when you say, I want 250 machines here, you just get them. The blue line is an approach where we said, OK, fine. Whenever machines become available, we will load data into them, and we will start running the algorithm as if that was all the data we had. And whenever we add some more data, some more machines, we just make them part of the next iteration, right? We just gradually increase the training set size for this machine learning algorithm. And as you can see in this particular setup, this performs really well because it's known that for the early stage of a learning algorithm, a sample of the data set is good enough, and that's exactly what we have here. As a matter of fact, there is a literature on when you should increase the size of the training set voluntarily. What we do here is we just don't do it voluntarily. We just have the system be the source of that decision. So we can get done, in this case, to a pretty good level before the alternative can even start. I think that's a pretty strong result that suggests that integrating systems events into machine learning is a good idea, and that doing this on a platform that exposes them naturally instead of asking the system to hide them like MapReduce does, like Spark does, like Giraffe does, is a really interesting avenue. OK, quick wrap up. All the code is available on GitHub. It's Apache 2 licensed. The artifacts are available on Maven Central. So it's fairly straightforward to start doing something with REEF. We do have a time-based release cadence right now, where we say on the 21st of each month, there will be a release. And because there was Hadoop Summit in this month, the release in June will be slightly less many changes as in other months. So it's not based on a feature set that we do the releases. It's just based on time. Every 21st, whatever is stable at that moment in time will be the next version. The last version we released was 0.4 on May 21st. We know that it works on pretty much all the Hadoop 2.2 plus versions that we tried, or others tried. Windows, Linux, HD Insight, Hortonworks, Cloudera, Apache Trunk. It works everywhere. We compile against Hadoop 2.2. You can't run on earlier versions. At least we haven't tried. OK, there are a couple of things that are happening on REEF by other companies, other partners. Number one is Surf. That's a project done by South Korean Telecom with the Seoul National University, where they're looking at, hey, let's build a caching service on top of Yarn and make it elastic, right? The more data comes in, the more containers you request and run that. And they are building this on top of REEF. And there's a project website, and Gorn can talk much more about that than I. The other research effort that's going on is Groupers, where the question is, can we unify all these notions of reduce and shuffle and the MPI reduce, MPI all reduce into one concurrent system? OK, that's it. We do have a website. Please go there if you have questions and all that. And we have a mailing list. Send us email. Patch is welcome. We hope that we will be at some point an Apache incubator project to make that a little easier. Thanks. And now we have 6 minutes for questions if this clock down here is correct. Or 6 minutes of awkward silence. Yeah?
So just in terms of scope of what you're trying to achieve, how would you say this compares to TES?
How this compares to TES? TES is, in some sense, a layer on top of REEF. If you think about a layering setup, right? TES has to solve all the problems that we solve, right? They have to figure out when machines disappear and all that. But when you use TES, you also have to subscribe to a DAG of your application, right? It's a DAG scheduler. You need to have operators. They form a DAG. The machine learning example that I gave doesn't form a DAG. It's just machines that start communicating with each other. So it's a lower level abstraction. REEF is a lower level abstraction than TES. And the same is true for Spark, Hadoop, and all the others, right? The question that we asked ourselves when we started REEF is, what is the thickest layer on top of Yarn that we can do without having the users buy into a particular programming model, right? And Tez is clearly on the other side of that because it says, hey, if your job is a DAG, we can do an awesome job for you. If your job is not a DAG, then, well, use something else. Right? Yeah.
Do you know if the accuracy of a classifier suffers if you're basically doing a model training, like partition on a bunch of machines as compared to just doing it on a single machine where all the training data is available?
So in this particular learning algorithm, there's no difference. If you had all the data on all the machines and you would run the same computation as on a single machine. There are other algorithms, like if you run stochastic gradient descent, where the order in which you visit the examples matters a lot, where it gets much more tricky. So, but you can design algorithms that can work well in this regime. More questions? Yeah. I have.
You mentioned before that you wanted to bridge
Yes.
JVM and
Yeah.
the .NET side of things. So here's your chance to tell us what
Yeah. So the feature that we currently have is the driver. Let's say you have a Java driver and you want to have a computation where part of the computation is .NET, the other part is JVM, and the third part is Python. We haven't written the Python code, but it's very conceivable. The protocol between the driver and the various evaluators is just protocol buffers, right? Everyone can implement that. And you can write applications that then have half of their computation in .NET and half of their computation in the JVM. Now, on the driver itself, the core of REEF is always Java, but we bridge it within the same process into the CLR. So the event handlers that make up the user code in the driver can be either in Java or in .NET. And then you can have either a .NET driver orchestrating a Java process or a mixed process, or you can have a Java driver orchestrating a .NET process. Now, in order to make this sane, we have Tang on both sides for our configuration management. And as I was saying earlier, we have code that makes it so that when you write a configuration for a .NET process, we can have Java code that tells you whether or not this is sane, whether the CLR will be able to instantiate these objects. So we externalize the type system and do a lot of very intensive things there. So the reason that we have the evaluators in multiple languages is exactly that. Because in your data flow, you don't want to continuously serialize, deserialize data just to go across the two runtime environments. So that's why we re-implemented them. On the driver side, there isn't much performance loss because the event rate that comes in is easily handleable by our JNI pinvoke setup. Okay. 3, 2, 1. We're done. Thanks.